Howdy. We are working on the project Transforming Reinforcement Learning, Solving Partially Observable Markov Decision Processes with Transformers. DQNs have proven to be effective in playing games, for instance, Atari games, where the inputs are fully observable frames from the games. However, in the real world, we may not always have the complete state information available. Our goal in this project is to learn the optimal policy in such a space where we have limited observability of the environment. Thus, we formulate reinforcement learning as a sequence modeling problem. We propose a deep reinforcement learning model that incorporates transformers to solve a partially observable Markov decision process problem. In this project, we initially implement deep recurrent queue networks on POM-DP and use the obtained results as benchmark to compare with deep transformer queue networks on POM-DP. So what's the motivation? Well, while RNNs and LSTMs are used for sequence modeling problems, transformers have the ability to capture long range dependencies in sequential data. Through the technique of self attention mechanism, transformers learn observations and actions that are most relevant and use the only valuable experiences which are useful in POMDP. Also, transformers have the ability to adapt to different types of POMDPs.
Moving on, let's look at the application of transformer based queue network. It can be used in various fields such as robotics, autonomous driving, finance, etc. For example, in the case of autonomous driving, we can consider the partially observable state as when the roads are obscure. In our project, we are currently using our implementation to solve a partially observable carpool environment from the OpenAI classic control environment. The environment considered is cartpool version 1. Talking about the environment, a cart moves along a track and a pendulum is placed upright on the cart, and the goal is to balance the pole by applying forces in the left and right direction of the cart. The MDP formulation consists of the following. First is the action space, where the cart can be pushed to either the left or right. The observation space has four components: cart position, velocity, pole velocity, and pole angle. The table gives the range in which these components have their values. Since the goal is to keep the pole upright for as long as possible, a reward of +1 for every step taken, including the termination step, is allotted. We have implemented two POMDP scenarios. In the first partially observable case, we only consider the cart position and pole angle, hiding the velocity of the cart and pole angular velocity from the agent. In the second case, we use a mask to hide different observation space components at different iterations, thus forming a partially observable environment. We currently analyze the performance of deep recurrent queue network on both the scenarios and aim to extend to more partially observable environment in the future.
Now, moving on, let's look at some of the existing work that's been done on this topic. In the past few years, there has been a lot of interest in applying deep learning based methods to solve problems in reinforcement learning. With the DQN model to solve partially observable MDPs, it is required to keep track of the previous observations in order to do well on the task. However, this has certain challenges like the huge memory requirements that are required to keep track of, store the previous observations. So it is important to predict the Q value based on the current observation alone. This is where this paper on DRQN or Deep Recurrent Queue Networks by Matthew Hosnack and Peter Stone comes in. Their idea was to use a LSTM network to capture the long-term dependencies between the observations and not rely on using the previous observations along with the current observation at each time step. One difference in terms of training between DQN and DRQN is that in DRQN, the samples are generated from the episodic memory. This means that all the samples in a batch belong to the same episode. Now let's look at the model architecture. In the DRQN paper, they use the architecture shown here. They use a model with CNN layers followed by LSTM network. They use CNN because they deal with environments which generate image-based states. Uh, so since we are dealing with a card pool environment, which generates or gives states in the form of numerical vectors, we are using a model with linear layers to instead of the CNN instead of the convolution layers, and a LSTM layer to keep track of the temporal dynamics of the environment.
We have conducted experiments with mainly 4 different model environment combinations. First, we used a conventional DQN with MDP process where the agent has access to complete state information from the environment. Second, we used a DQN with POMDP process. Third, we used DRQN with POMDP where agent has access to just the card's position and pole's angular position while the velocities are masked. And finally, we use the DRQN with random mask where one of the state's component is randomly masked and fed to the agent as observation. As expected, DQN with full state access gave near perfect rewards, and this is our benchmark to compare against. DQN with POMDP gave the worst rewards among the experiments, and this is not surprising due to the fact that here partial observations are treated as proxies for state information. DRQN with POMDP, however, showed significant improvement over DQN. Also, we noticed that DRQN with random masking performs better than DRQN with fixed state components being masked. At this moment, we are not quite sure why this happens. So far, we have seen approaches to solve the POMDP problem by using either the observation as a proxy for underlying true state or by using the agent's history as some sort of memory to look back into while making a decision. The first approach gave us very bad results as evident from DQN's reward plot in the previous slide. For the memory-based approach, DRQN introduces memory in the form of recurrency using RNNs. In this case, we use LSTM. However, in the earlier slide, we have seen that the performance of LSTM-based network is not very good when compared against the benchmark MDP. Training LSTMs also take a lot of time as the back propagation is done through time steps. The inputs are fed sequentially as the time steps roll forward. As a result, LSTMs are quite slow. Transformers, however, are faster in the sense that the attention mechanism that is used in the transformer can be parallelized because the entire input sequence is fed into the network at once. Transformers are ubiquitous in NLP, and since they are known to be effective in encoding sequences better than RNNs, therefore, we are going to use Transformers encoder architecture to encode an agent's observation history as it takes action in the environment. So, our plan currently is to first transform the agent's observations into tokens via embeddings and then pass the tokens into the transformer encoder. We are going to use self-attention to capture dependencies between observations. Finally, in the end, we are going to pass the observation representations through a feed-forward network with Q values as the output. We are also going to use the same episodic memory buffer that we used for DRQN to sample input batches. The objective we have is to achieve better performance than DRQN. We also plan to see the dependencies between observations by visualizing the attention scores so that we can see what memory the agent is referring to while taking the current action. For data generation, we also look to use grid-like environments where the environment's true state is the entire grid, but the agent's observation is only limited to its proximity. We are trying to find ready-to-use packages which provide this functionality. And simultaneously, we are also implementing our own environment, which provides this POMDP use case based on Frozen Lake from Jim. Thank you.